Welcome to another 2011 FRC LabVIEW tutorial. In the last FRC tutorial, we looked at the 2011 Vision Example program. In this tutorial, we will be importing this code into a robot project and replacing the base autonomous code with one that tracks the leftmost game pole and aligns the center of the robot with it. We'll begin by making some room in our robot project's vision processing VI, so that it can hold all the vision processing code from the example program. We'll do this by holding down the control button and drawing a box inside of the case structure that is large enough to hold the code. Now we'll go into the Vision Example program and copy what we need from it. First, we'll copy the two mask iMac create VIs by holding Control and pressing C on the keyboard. Now we'll go back to our robot project, hold Control, and press V to paste the code. We'll repeat this process for everything to the right of the vertical green line in the example program. Make sure that all of the code that was inside of the while loop in the example program is inside the true case of the outer case structure, because the true case will run when the Enable Vision button is set to true. Now we'll need to connect up the loose wires. We'll start by connecting the image out output of the WPI Camera Get Image VI to the image source input of the iMac Color Threshold VI. This is done because the image that is being analyzed will now be coming from the camera, rather than an image file on the computer. Also, wire the same image out output into the image input of the iMac Get Color Pixel Value VI, so that we can find the HSL values of the reflectors on the poles when we run the program. We'll also copy the threshold image display by pressing Ctrl-C, and then pasting it by pressing Ctrl-V, and wire the image out output into it as well. We'll rename this image display to Original, because this will be the original image that the camera sees. This is so that we can see the image that the camera displays on the front panel. We'll have to recreate the ROI property node for this image display as well, and replace the current one with it, so that the HSL values will be read from the camera's image display. We'll wire the new image outputs of both of the mask iMac Create VIs and the pixel measurements array to where they were in the example program. We can clean up the remaining broken wires by holding Control and pressing B on the keyboard. We are going to be tracking the leftmost pole, and to do so, the robot will need to know the position of this pole. The leftmost pole that the camera can see is always the first row of values in the columns array. Therefore, if we create an index array function and wire the columns array into it, the first element in it will be the first row of values, which will be the leftmost pole. If we wire this first element into an unbundleByName function, we will be able to take the mean value of the leftmost pole, which will be its center X position. With this X position, we will be able to determine where the leftmost pole is with respect to the center of the robot, and program the robot to turn in the appropriate direction to align itself with the pole. Note that we could also track the center or rightmost poles by using the array size information of the columns array. In order to know what pixel the center of the camera image is, we need to know the pixel dimensions of the camera image. This is set in two locations, in the Begin VI and in the Robot Main VI. The image size value in the Robot Main VI gets passed into a global variable. This global variable is read in the Vision Processing VI, where it is compared to a number, and if this number is not equal to it, the camera size is updated to be the value in the image size global variable. Even though the image size is set by this global variable, the image size should be set in both the Robot Main VI and the Begin VI, just to make sure it's the size you want it to be. The Vision Example program was designed to work at 320 by 240, so we will keep the image size as the default. Now that we know that the camera image will be 320 pixels wide, we can decide what the robot will do according to where the center of the leftmost pole is located. We'll divide the camera image into 3 sections: left, center, and right. The left side of the image will be from 0 to 130 pixels, and if the leftmost pole is in this section, we will want the robot to turn left to align itself with the pole. The center of the image will be from 130 to 190 pixels, and if the leftmost pole is in this section, we will want the robot to stop turning because it has aligned itself with the pole. The right side of the image will be from 190 to 320 pixels, and the robot will need to turn to the right in order to align itself with the pole. We will begin by creating a case structure and a less than function. We will wire the mean value of the leftmost pole into the x input of the less than function, and create a constant for its y input, and set it to 130, which is our left side pixel limit. Next, we'll wire the output of the less than function into the case structure. In this case structure, we are going to create an enumerated constant. An enumerated constant, or enum for short, is basically a list of string labels with corresponding integer values that you can select on the block diagram. To create the list, we will right-click on the enum and click Edit Items. In this list, we will need a value for each state that the robot can be in according to where the leftmost pole is. These states are center, left, right, and not found. Click OK, and the enum will update and contain each of the values we assigned it. The great thing about enums is that they can be wired into a case structure, and each value we assigned it will become a case. Then, we can probe the enum while the program is running to see which case we are in, and it will display the string value that we assigned it, rather than just an integer. This will make debugging a lot less strenuous. If we recall, we want the robot to turn to the left when the leftmost pole is to the left side of the camera image. Therefore, in the true case of the case structure, we will want to be in the left state. In the Vision Processing VI, we will only be telling the robot what state it should be in, not what it should be doing. That we will be doing in the Autonomous Independent VI. But in order for the state information to be read in the Autonomous Independent VI, we will need to use a global variable. There is already a global variable in the robot project called robot global data, and we can use it instead of creating a new one. We can access it by going to the Project Explorer and dragging it into the Vision Processing VI. In order to be able to store the state information within this global variable, we will need to copy the enum from our block diagram, then double-click on the global variable, and paste it into it. We'll rename the enum to be called Vision State, so that we know what it is when we use it. Now we can close the global variable and click Save to update it. When we left-click on the global variable, we will see that the vision state can be chosen. If we wire the enum into the global variable, we will be storing the integer value of the enum state in the global variable. Next, we will need to create another case structure within the false case of the existing case structure. This will be for our other two states, center and right. We'll create another less than function and wire the mean value of the leftmost pole into the x input. Now we'll create a constant for the y input of the less than function and set it to 190, which is our right side pixel limit. We'll wire the output of this less than function into the inner case structure. When the outer case structure is false and the inner case structure is true, the middle of the leftmost pole is at a horizontal pixel value which is not less than 130 but is less than 190. Therefore it is in the middle of the camera image, and so the enum state should be center. We can copy one of the previous enums by holding Ctrl and dragging it. Then we can place it in the true case of the inner case structure and set it to center. We will then wire this enum into the vision state global variable. When the outer case structure is false and the inner case structure is false, the middle of the leftmost pole is at a horizontal pixel value which is not less than 130 and also not less than 190. Therefore it is in the right side of the camera image, and so the enum state should be right. Once again, we can hold Control and drag one of the previous enums to copy it, and then place it into the false case of the inner case structure and set it to right. We will then wire this enum up to the vision state global variable. That covers all of the states the robot can be in when the leftmost pole is in sight. But what about when the camera doesn't see any poles? In the event that the camera does not identify any poles in the image, there will be no values in the columns array, and therefore it will be an empty array. With that knowledge, we can use a function in the comparison subpalette called emptyArray. We can wire the entire columns array into it, and create a case structure around everything that we just created. We can then wire the output of the emptyArray function into this case structure. If the array is not empty, and the camera has located at least one pole, the emptyArray function will output a Boolean value of false, and therefore our previous code should be in the false case of this outer case structure. We can change the case that the code is in by right-clicking on the selector label of the case structure and clicking Make this case false. In the true case, the camera has not found any poles, and so the robot should be in the not found state. We'll copy one of the enums again by holding down Control and dragging it, and then place it into the true case of the outer case structure, and set it to not found. We'll wire this enum up to the vision state global variable as well. The robot should be in the not found state if the camera is not enabled as well. We will need to copy one of the enums again, and place it into the false case of the outermost case structure. We will then set this enum to not found, and wire it into the vision state global variable. Now that all of our states have been created in the vision processing VI, it is time to go into the autonomous independent VI and program the robot's actions in each state. We will begin by clearing all of the code from inside the while loop, except for the arcade drive VI and the wait function. Next, we'll pull the global variable into this VI by dragging it from the Project Explorer. We'll right-click it and click Change to Read, because we will be reading the state in this VI. Next, we will create a case structure and wire the vision state global variable into its case selector terminal. In the left state, the leftmost pole will be to the left of the robot, and so the robot will need to turn left. We'll create a constant for the x-axis value of the arcade drive function and set it to -0.5. We will need to drag this constant into the left case and wire it back up to the x-axis input. We will want the loop to continue running when the robot is in this state, so we'll create a constant for the loop condition terminal and set it to false. Now we will drag this Boolean constant into the left case and wire it back up to the loop condition terminal. Instead of repeating this whole process for each case, we will right-click on the case selector, click Remove Empty Cases, and then click Duplicate Case until each of the states is populated. Now we can set the values in each case without having to create constants for each one. In the center case, we will set the x-axis value to 0 because the robot is aligned with the leftmost pole, so it should stop turning. We will set the loop condition terminal to true because the robot has found the pole and therefore the program has achieved its objective, and this while loop can be exited. In the not found case, we will set the x-axis value to 0 because the camera cannot find any poles, and so the robot should be stopped. Note that we could also tell the robot to turn in either direction in this case, so that it might find the poles. We will set the loop condition terminal to false, to continue running the loop in case the camera finds the leftmost pole again. In the right case, we will set the x-axis value to 0.5, because the leftmost pole is to the right of the robot, and so it should turn to the right. We will set the loop condition terminal to false, to continue running the loop. We want the robot to align itself with the leftmost pole, not to travel towards or away from it, so we'll create a constant for the y-axis value of the arcade drive function and set it to 0. To see the program in action, connect to your robot and run the program in robot main. We'll need to look at the vision processing front panel in order to determine the HSL values for finding the reflective tape on the poles. We can then probe the vision state enum in order to see which state the robot is in depending on where the leftmost pole is. As we can see, the robot will track the leftmost pole and align itself with it. Keep in mind that all of the camera settings in the Begin VI can be changed to optimize the performance of your camera, and that the HSL values should always be calibrated when running the program in a new environment. This tutorial used the 2011 Vision Example program to align the robot with the leftmost game pole. But this is only one way in which the code can be used. For example, the 2011 Vision Example program can be used with the base autonomous code to track the poles when the robot is at the end of the black line. Or it could even be used in teleop mode to align the robot with the pole before it places an inflatable tube on it. The possibilities are endless, and each team should try using the 2011 Vision Example code in different ways in this year's competition, and see what they can come up with. Thank you for watching this tutorial, and good luck in this year's FIRST Robotics competition.